It turns out that the stars are formed in so-called giant molecular clouds. And this is a famous Hubble Space Telescope photograph of an example of part of giant molecular cloud. What is shown here are these so-called pillars of creation. These are columns that are protruding out one huge giant molecular cloud. And here, as I'll explain later, we have direct observational evidence that stars indeed get formed in these giant molecular clouds, because their diameter ranges from 15 to about 600 light years across. Okay? And as I pointed out earlier, these columns here, the one on the left, its height is 1 light year from the top to the bottom. Okay? So you can appreciate how large these structures are. Turns out that they are dense enough, and the dust in such cloud blocks the starlight from surrounding stars, so that the temperature in the interior is cold enough that the hydrogen atoms bind into hydrogen molecules. Okay, so simply the electrical forces manage to combine two hydrogen atoms to form a single entity, hydrogen molecule, which consists of two hydrogen atoms. Now, it turns out that the material within this cloud is not distributed uniformly. There are clumps of higher density. Okay, so if this region here is a giant molecular cloud, there are pockets of higher density. Okay, so this schematically illustrates the existence of these clumps. And if you go to the actual photograph of that particular nebula M16, by the way, it stands for Messier Object 16. Centuries ago, astronomers were fascinated by watching comets, and they noted that there are some fuzzy regions in the night sky that were bad to point their telescopes in those directions. So what Messier did, he actually located all of these and put them in catalog, and this particular one had the catalog number 16, so therefore it is M16, and of course much later with the Hubble Space Telescope we found out what these diffuse regions in the night sky really are, right? But you can see on this Hubble image that indeed there are clumpy regions that have been exposed as the UV radiation from very hot surrounding stars evaporates the surface material of less density. So what it exposes are these clumps of more dense material. So indeed, it's not that we are guessing that these clumps exist, but indeed we have observational evidence that they are there. Okay, and the question is, how do and why do these clumps form? And one possible scenario, although probably there are more, is that if there is a nearby massive star that ends its life in a huge explosion, type 2 supernova, that the shock waves from the explosion actually, as they pass through this cloud, create the clumps, which in turn results in these clumps as the shock wave passes through the cloud. Okay, and let me just show you, I've linked under the study aids a little animation from NASA that illustrates what I'm talking about. See, there is this cloud, a massive star goes supernova, the shock wave passes through the cloud, creating clumps that will eventually result in the new stars. Okay, so what happens is that those clumps that are dense enough will start collapsing under their own gravity. They start gravitational contraction. And as they contract, as the material falls in, that clump starts heating up. So in this process, the gravitational energy is being converted into thermal energy as the clump contracts. Not really. But anyways, you get the point. So this is one such dense clump. And as it contracts, it heats up, as I've tried to indicate by this reddish color. So what is being formed here is so-called protostar. Protostar is a star to be, not full-fledged star that is fusing hydrogen into helium, generating its energy that way. It is heating up because of gravitational contraction. Now, this process where gravitational energy converts into thermal energy actually operates everywhere in the universe. If you would go to Niagara Falls nearby and measure the temperature of the water just before it comes down the falls, and then measure its temperature when the water has fallen down, you would notice that it's slightly warmer. And there again, you have an example that the gravitational energy, as the water is being pulled down by the Earth's gravity, is converted when it eventually slams into the mass of water at the bottom of the falls, that its temperature slightly goes up as a result of this conversion of gravitational into thermal energy. Okay? So that is a general principle, and basically this gravitational contraction is causing this clump to get, first of all, more dense, but also it heats up. So if the clump had enough mass so that the temperature in the core of the protostar reaches at least 10 million degrees Kelvin, then the nuclear fusion of hydrogen into helium will start. A degree Kelvin is another unit for measuring the temperature. It's basically, it's 0 corresponds to minus 273.16 degrees Celsius, right? Or Celsius 0 corresponds to 273.16 Kelvin. But when the temperature is expressed in the millions of degrees, that shift of just under 300 is irrelevant. So it doesn't really matter. You can say Celsius here, because the difference between Kelvin scale and Celsius scale is irrelevant for these values of temperature. And the protostar will soon, after some period of instability, enter the main sequence stage, and the protostar becomes star. And it turns out that if the larger the mass of the clump, the faster it will contract and become a main sequence star. So this so-called protostar stage is shorter for higher mass stars, and vice versa. And it's longer for the lower mass stars. So here you can see what I'm talking about on this schematic presentation of what happens to stars of different mass. Those that are very massive will eventually, they will reach high temperatures, and the energy production rate is going to be very high, and they end up at the top of the main sequence. The star like our Sun of 1 solar mass will end up somewhere in the middle of the main sequence, and then a low mass star of about half solar mass will end up near the bottom of the main sequence star. Okay? And it turns out that for a mass like, for the star like this one, of 15 solar masses, this entire protostar stage, as it is contracting, lasts maybe 100,000 years or so, right? And as the mass is reduced, the time becomes much, much longer. It takes longer for the star to contract. For this one here, the contraction period lasts 160 million years. For the one that has a mass of 5 times the mass of the Sun, it is 700 million years. A star that has a mass of 2 solar masses, the contraction period is about 8 million years. And for a star of 1 solar mass, like our Sun, the protostar stage lasts about 30 million years. And for a star whose mass is a half mass of the Sun, it is 100 million years. Okay, so indeed you see that the more massive the star, the shorter is that protostar stage, because everything happens much more quickly. Because of the large mass, the object contracts much more quickly than if the mass is reduced. Now, I should also point out that we can observe the protostars. They are typically hidden in the interior of a giant molecular cloud, right? We can't see those protostars that are in the interior of those columns. But once they become hot enough, we can observe them again in infrared, because their elevated temperature causes them to shine at infrared wavelengths. Okay? But not from the very beginning. They have to become hot enough. So there is a line that parallels the main sequence that is often referred to as the birth line. Right? So once the protostar crosses this birth line, once its temperature is high enough, because as they contract, their temperature, as you can see, increases all the time. But once it gets hot enough, that is such that it crosses this birth line, then we can see them at infrared.